Okay, let's go over some AP table problems. So the first one, you are allowed to use a calculator. I'm not going to use it for this, but I still wanted to do this one with you because I think the concepts are important. So anyway, things to notice about this, they give you the temperature measured in degrees Fahrenheit at certain times. And they do say that your function is strictly increasing, twice differentiable. So even though you only see a few points on this graph, you know that the rest of the function that you can't see, the function's continuous, because if it's differentiable, it's continuous, and it's increasing. Okay, so then they heat the water for 30 minutes, and they take the measurement of the temperature at different times for the first 20 minutes. Okay, let's get to our first problem. Let's see if I can do this. Using the data in the table, estimate W prime of 12, right? We know the derivative is the slope of the tangent at 12. Well, we can't do it. But if we can't get the derivative with a table problem, you approximate it with the slope formula, the slope of the secant. And the points you pick have to be as close to 12 as possible. So we'd have to use 9 and 15. So instead of getting the actual value of dw dt at t equals 12, we're going to approximate it with delta w over delta t. So we're going to do the difference in w values. So let's say 67.9 minus 61.8 over 15 minus 9. All right. Now, you can leave your answer like that if this was the AP. For those of you that are interested, and these people had a calculator, it was 1.017. The units for dw over dt would be units of w over units of t. So it would be degrees Fahrenheit per minute. Now, they did not, let's see. Using correct units, okay, interpret the meaning of your answer in the context of the problem. So what that's telling you is that the water is increasing at a rate of approximately 1.017 degrees Fahrenheit per minute when t equals 12. Okay, I'm not going to write all that, but that's what it would mean. Okay, now let's go down to the second problem. B. Use the data in the table to evaluate the definite integral from 0 to 20 of w prime of t dt. So you see this, don't panic, because you might say, well, I don't know what w prime is. I only have a few points on w. Think about what you would do to evaluate a definite integral. You would get the antiderivative, which would be just w of t, right? And then you would plug in the upper limit and the lower limit and subtract. So w of 20 is 71. W times 0, I'm sorry, I'm looking at my chart here, is 55. And 71 minus 15, again, leave it, but you know, just to show you, we could write that as 16. So remember what you get, because they want you to interpret the meaning of this. Whenever you integrate the derivative of a function, you get the total change in that function. So that gives you the temperature change of the water from time 0 to 20 is 16 degrees. So, so the temperature, the total change in temperature of the water is 16 degrees from t equals 0 to t equals 20. Okay, let's try C. That's what you'd have to say, though. I'm just trying to save time doing this. All right, the next part, trying to see where I am. Okay. The average, for time 0 to 20, the average temperature of the water is, okay, that we recognize this. That's how you get the average value of a function. Use a left Riemann sum with 4 subintervals indicated by the data to approximate it. All right. Now, first thing you look at, these points, they're not evenly spaced between 0 and 20. So they're all going to have different widths. So left, ream, and sum, we're going to use rectangles, but we're going to do width times height plus width times height for each rectangle. Okay, I can go back up here now. Okay, so we're approximating this. So for the first rectangle, see how the t's go from 0 to 4? The width is 4, and it said left ream and sum, I believe. Yep. So for the height, we'll use the 57.1. Plus the area of the next rectangle, the times go from 4 to 9. So that would be 5. Oh, wait a minute. I said left, and then I put down the right. Oops. All right. Sorry about that. Yeah, for the first rectangle, the width was 4, but we're using the y on the left, so it's 55. I hope I didn't freak you out with that. Okay, the next rectangle, times go from 4 to 9, so that's a width of 5. Using the height on the left, that's 57.1. Okay, then we move on. Next, the times go from 9 to 15, so that's a width of 6, and we use the 61.8. That's right here, right? So it goes from 6 times 61.8. And then the last rectangle, the times go from 15 to 20, so that would give us 5 times, and we're going to choose the y on the left, which is 67.9. Now, you would leave your answer like this, like don't try to figure it out. For those of you that were trying to figure it out, I'll just let you know for your own sake, that's 60.79. So that's the first part of this problem. But they also want us to, okay, so we approximated that. Does this approximation overestimate or underestimate the average temperature of the water over the first 20 minutes? Okay, so we got the average temperature of the water was 60.79 degrees Fahrenheit, right? Because that's what that is, how to find the average value of a function. Remember this function they told us here was increasing. When you have an increasing function and you've got a left ream and sum, that's going to give you an under approximation. So we would have to say in our work, the approximation is an under approximation because the function is increasing, because W is, they told us, let's see where they said it, strictly increasing. All right. Okay, then the last part of this question, so the table gives us, the temperature of the water from time 0 to 20. But now the last part of the question, they always seem to like go off somewhere. For times between 20 and 25, the function W that models the water temperature has a first derivative given by W prime, and they give you that equation. Based on this model, what's the temperature of water at time t equals 25? Well, if you wanted to get the water temperature at time 25, you would have to start with the water temperature at time 20, which is, oops, I'm not in the screen, 71.0, and add the change in water temperature, which you get by integrating W prime of t from the old time to the new time. So this would be something, they gave you a formula for this. You would just put this into your calculator and do math 9. So you did 71 plus math 9 on that. And for those of you that are interested, this is 2.043, and it would give you a value of 73.043. I don't think they're going to do something like that this year because it sounds like you can get away this year with a 4-function calculator. Okay, so that was the first problem, 2012. 2013, let's see what we have with this one. 2014. Okay. right, so this was a no calculator question. And let's see what it says. Hot water is dripping through a coffee maker. The amount of coffee time T, so they're giving you the amount of coffee at different times, measured in ounces. But it's given by a differentiable function. So if it's differentiable, it's continuous. So these, you don't have to worry about anything weird happening between these points. The graph continues, right? There are no holes or jumps or asymptotes. Okay, so C for coffee is measured in ounces and T for time measured in minutes. Selected values are given. All right, first one. Use the data to approximate the derivative of C at 3.5. Well, again, you can't get the slope of the tangent with a table problem, but you approximate it with the slope of the secant. Okay, so again, you're approximating dc dt at t equals 3.5 with the change in C over the change in t. So 3.5, if you look at our table, we're going to have to use these 2 points. So 12.8 minus 11.2 for the change in C over 4 minus 3. Okay. So this actually comes out, I would leave it like that, but you know, if you want to, you can say it's 1.6. Now the units, do they say indicate units? Yes. Would be the units of C, which would be ounces. Oops. Per units of time, which is in minutes. All right, let's try a second problem. Part B. Is there a time where C prime of t has to equal 2? Justify your answer. Okay. You know, if you see, does the function have to equal value? That's intermediate value theorem. Does the derivative have to equal a particular value? That's mean value theorem, which says as long as the function is continuous and differentiable over the interval, right? Continuous over the closed interval, differentiable over the open interval, then the slope of the tangent, the derivative, has to equal the slope of the secant for some value of t, in this case between 0 and 6. So the first thing, oh, wait a minute, it said, is there a time between 2 and 4? So I would have to then find the slope of the secant from 2 to 4. So let's find C of 4 minus C of 2. So we're just using the slope formula to find the average rate of change from 2 to 4 over 4 minus 2. Let's get what that is. So that's 12.8 minus 8.8 over 2. Lo and behold, that's 4 over 2, that's 2. So you just figured out the average rate of change is 2. And since this function meets, is differentiable over the interval, we can say by the MVT, there must be some time, what's they call the t in the problem, t, where t is between the endpoints that we used, such that C prime of t equals 2. And that's all you'd have to do. So anytime that they say, does the function have to equal a value, that would be intermediate value theorem, right? It's got to take on all values between the y's of the endpoints. But does the derivative have to equal a certain value over an interval? Find the slope of the secant of that interval. And as long as the function's differentiable, the derivative would have to equal that value for some independent variable between the endpoints. Okay, part C. All right, let's see where we are here. Okay. Use a midpoint. Use a midpoint sum with 3 subintervals of equal length indicated by the date in the table to approximate the value. Oh, once again, they're doing the average value of a function. 1/6 the definite integral of a function. That's the average value of that function, right? This is what they want us to approximate. Now the 1/6 stays, right? But for the approximation, let's see, we're going to be using a midpoint sum with 3 subintervals of equal length from 0 to 6. Okay, so the width is going to be b minus a over n is 2. All right, now, so for the first, so the width is going to be 2 for all of them because they're evenly spaced. But now I need to figure out my 3 heights. So the first rectangle, the times go from 0 to 2, right? Because that's the width is 2. So for the height, we're going to use the y of the midpoint, that's 5.3. Plus, moving on to the second rectangle, the times go from 2 to 4. So we're going to use the value of c at 3, which is 11.2. And then the last one, we'll use c of 5, which is 13.8. So what's in here, that's my rectangle approximation, but they asked us to approximate it with the 6th outside. So I would leave my answer like this. It does come out to be 10.1, and the units for this, for the definite integral, remember you multiply units. Integrating. This is the average value of c when we integrate this. Oh, because the, wait a minute, ounces time. Oh, this out here, that's the difference in time, so the time cancels, so it is ounces. Sorry. And hopefully you would recognize, oh, that's just the average value of the function c over this interval. And they actually want us to explain what that tells us using correct units. Okay. Anytime you get the average value of a function, it has the same units as the function itself. Explain the meaning of it in the context of the problem. So it's just the average amount of coffee in the cup from time 0 to 6. I shouldn't use the word it's. I should rewrite this. The average. Remember they told us that C was the amount of coffee in the cup, so it's the average, instead of just saying the value of C, amount of coffee in the cup over the interval T from 0 to 6. I'm sorry. All right. Now one more problem, and this one, and that's D. Let's take a look at D. See, look at this. They come in with something weird at the end. The amount of coffee in the cup in ounces is modeled by some function. Here it is. Using this model, find the rate at which the amount of coffee in the cup is changing. So that's the amount of coffee in the cup, and they want to know the rate at which it's changing when t equals 5. Well, the rate of change of a function is just the derivative. So what they're really saying is find the derivative of that function when t equals 5. So this was a no calculator question, so we do have to take the derivative. So if b of t equals 16 minus 16e to the negative 0.4t. Okay, the derivative of t is 0, so I won't write that. Then I have that minus 16 is a constant multiplier, minus 16. To take the derivative of e to the u, it's e to the u, so I just copy it, times u prime, the derivative of the exponent, which is times negative 0.4. So there's the derivative, and now we just got to plug in 5. So b prime of 5 would be negative 16 e to the negative 0.4 parentheses 5 times negative 0.4. Now the units of the derivative of b, which is just like c, it's measured in ounces, would be ounces per minute. I keep forgetting my u there. Ounces per minute. Okay, and I would leave your answer like this. If you wanted to simplify it, but don't do that on the AP exam, it'd be 6.4 over E squared ounces per minute. But I would just leave my answer like this big mess here. Okay, so that was the second AP problem, and that was from 2013. I want to do one more with you. We're doing them pretty fast. This is 2014. This is another no calculator. I do think tables are really important on the AP. They love them. This year? Who knows? Okay, I'll use this piece of paper. Oh, this one gets a little crazy. They bring in some other topics, but it's good review for us. So this is 2014. For different times, they give us the velocity of train A, measured in meters per minute. I was going to make sure that this function is differentiable. Yeah, there it is. That means it's continuous. Okay, so velocity is measured in meters per minute, and at different times measured in minutes, they give you the velocity for train A. All right, let's get right to A. Find the average acceleration of train A over the interval. So that means another way of thinking, acceleration is the derivative of velocity. So we can approximate the acceleration is dv dt. This is instantaneous acceleration, dv dt. We can approximate that with the average acceleration by taking dv over, oops, this eraser's not good. So this is instantaneous acceleration, right? Derivative of velocity. So average velocity would just be change in velocity over change of time. So let's see what that's going to be. Over the interval from 2 to 8. So at 8, the velocity is negative 120 minus the velocity at 2, which is 100 over 8 minus 2. Now again, you could leave it like that. I'm going to clean it up for you. That turns out to be negative 110 over 3. The units for this would be the units of velocity, which is meters per minute, over the units of time over minutes. So meters per minute squared. Yeah. All right. Looking on to B. Do the data in the table. Sounds weird, right? I guess that's plural and singular. I'm not sure about that. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time? So they want to know, does it make sense that the velocity of the train is negative 100 for some time between 5 and 8? Look at these velocities between 5 and 8. They go from 40 down to negative 120. This function's differentiable. If it's going from 40 to negative 120, doesn't it have to be negative 100 for some time between 5 and 8? Yes, it does. And you're going to get through this one by citing the fact that it is continuous. If you're going to use the intermediate value theorem, you got to say it's continuous. All right, so since v A of t is continuous, maybe I would say differentiable and therefore continuous, by the intermediate value theorem, there must be some time t where t is between 5 and 8. Actually, I don't need to include the endpoints. T is between 5 and 8, such that VA of t equals negative 100. Oh, you know what I didn't put in here? Negative 100 is between negative, okay, wait a minute. I'm going to say right above here. Okay, negative 100 is between negative 120 and 40. Okay. There we go. That's good. All right, therefore, by the intermediate value theorem, there's a time t between 5 and 8 such that VA of t equals negative 100. Okay, good. Now let's go on to C. At t equals 2, train A's position is 300 meters east of the origin station, and the train is moving east. Okay, just so you know, guys, this is going to turn in, oh no, it isn't. This isn't. Okay, sorry. Okay, train is heading east. So let's just think about this. At time 2, all right, we already know it's, this train is running back and forth an east-west train, east-west track, right? And its velocity at time 2 is 100. So it's moving to the right. And it's 300 meters east of the station. So like this is 300 meters east of the station. And it's moving east, yes. Write an expression involving an integral that gives the position of train A at time 12. Okay, so if we want to know, we know its position at time 2 is 300, right? That's what they gave us. Oops. And now they want to know what's its position at time 12. So we're going to use the fact that to get the position at time 12, it'd be the position at time 2 plus the change in position, which you get by integrating the derivative of position, which is the velocity, from time 2 to 12. So the position at time 2 is, no, this is going to be, we're going to approximate this. So we're going to take the position at time 2, which is 300, and then the part that makes an approximation is this. They want us to get this definite integral approximated with a trapezoidal sum with 3 subintervals. Now these are not evenly spaced. So remember, when you're using the trapezoids, you have to pull the half out. And if they're not evenly spaced, you're going to have to do the height times the sum of the bases for each one. And this is, we're going from 2 to 12. So actually, don't even think about the 0 here, because we're only going from 2 to 12. Okay, so for the first trapezoid, the height is 3. The sum of the bases are 100 plus 40. Oops, got to get in the frame here. Can't fit it all in. Okay, that's good. Okay, for the next trapezoid, times go from 5 to 8. So that's 3. Sum of the bases is 40 plus negative 120. And then the last one, times go from 8 to 12, so that's 4. And then negative 120 plus negative 120 plus negative 150. Sorry, that's kind of messed up. Now, let's see what we got here. So we have the 300, that was its position at time 12, plus the change in position, which we're approximating with trapezoids. So it's going to be 300 plus, this whole thing comes out to be negative 450. So it's approximately negative 150, the position at time A. All right. So since it came out to be negative, now let me see how they say to explain it. So that would be fine, but just so you realize, the fact it came out to be negative just means that the train is 150 meters west of the origin. Okay, the last one, I'm going to get out another piece of paper. For this last part is where it turns into a related rates problem. A lot of times it just like changes. And this year, you guys, it's going to be changing a lot for you. since I only have 2 questions, they're gonna switch off. A second train B travels north from origin station. That's so clever, okay. At time t, the velocity of train B is given by, now they give you an equation for this. All right. And they tell you at time 2, it's 400 meters north. So the position is positive 400 meters north of the station, and they give you the velocity of train B. Okay, find the rate in meters per minute at which the distance between A and B is changing at time t equals 2. Okay, so if you recall, so we have, remember at time t equals 2, they told us A was, when t equals 2, this is train A, it was 300 meters east of origin, and at time t equals 2, the position of train B is 400, okay. Now, let's call this distance B and the distance from train A to the origin A, and they want to know at what rate is this distance between train A and B changing. So first we write, and we'll call that distance C. So first we write an equation, A squared plus B squared equals C squared. Put that in there. We're going to take the derivative of both sides with respect to t. So 2a dA dt plus 2b dB dt equals 2c dC dt. I always get rid of the 2's, divide both sides by 2, that's legal. And now we're going to plug and chug. So at time t equals 2, A was 300. dA dt, the rate at which A's position is changing, if I get that right from the table, that's the 100, it's velocity. Plus B, which is the distance from the origin to train B, that's 400. Now, to get the velocity of B, dB dt is the velocity of the position, I have to plug the 2 into this right here. So now normally I would just leave it all. I would leave -5 times 2 squared plus 60 times 2 plus 25, but I'm going to run out of room. So the velocity at time 2 is -5 times 2 squared plus 60 times 2 plus 25. 2 squared is 4, so that would be -100 plus 120 plus 25. So this would be 20 and 25, that's 45 meters per minute. So that's what I put in for B. And then we're trying to figure out dC dt. I have to figure out what C is at that moment. Well, at the moment, when this side of my triangle is 300 and this side's 400, this is just a 3, 4, 5. C would be 500. And then we can figure out dC dt. Sorry. There we go. All right, so we've got, you know what I would do if I were you? Let's just go like this, 500, just put this whole side over 500. That would be, you could leave your answer like that. Do they say anything about units? They already tell you the units would be meters per minute. So you can leave it like that. And that is it for AP review of tables.